Just very quickly on the spectroscopy of alcohols, we're all very familiar at this point with what the IR of an alcohol looks like. All right, look for the broad OH stretch up from 33 to 3600, no problem. NMR, because oxygen is electronegative, any nucleus near it will be shifted to the left, so it'll be deshielded. So in C13, carbons will be shifted to the left, right, 50 to 80 or so. In proton NMR, the hydrogen bonded to the alcohol carbon, right, will be 3.5 to 4.5. So what I'm talking about is one of these guys, right? The H's bonded to the C that has the OH. Okay? Those will be 3.5 to 4.5. Okay? The OH will usually be broadened somewhat. Its chemical shift is not really predictable. It varies from alcohol to alcohol and concentration and things like that. But the key is if I add D2O to a sample, I'll replace this acidic hydrogen with D, and that broadened peak will disappear. So the OD bond is a little stronger than the OH bond. So we can titrate in just a little bit of D2O, look for what peak disappears, and that's the OH peak. For mass spec, review up on alpha cleavage, right? Break the CC bond closest to the O, leave the carbocation on the carbon next to the O, right, because it's resonance stabilized. Kick out the radical, right, which doesn't show up. So this carbocation that stabilizes reserve that is observed, that's often the base peak or the tallest peak. Dehydration is also very common, so look for 18 subtracted from the molecular ion, and that's water that's left, just like a normal dehydration reaction.